Okay, let's move on to dark matter. And what did I say? I think the mathematicians are full of dark matter. Okay, that's what I really think. Okay, okay. So what do we have here? What is dark matter? Well, dark matter is dark, and I showed you what it looked like. It looked like black. Okay, the other day, and it looks like that. What's underneath the green letters? Okay, but I call it the dark matter conundrum. Okay, I think mathematicians have this conundrum. What is this problem? Well, it starts here. Okay, so let's go slowly so that you see if you can follow along. Okay, so what is it? Let me get this in here. They put centripetal force equal to gravitational force. So we have centrifugal, towards the center of the galaxy, and centripetal going out to the out, flying away from the galaxy. And you have all these stars going around the galaxy, and they're pulled into the center of the galaxy by something called gravity. We don't know what gravity is, but somehow these stars are pulled. I hate to use the word pull because that already shows bias, but I have to use the word pull because everybody calls gravity a pull. I think ever since the days of Newton, everybody calls it a pull and then uses particles to prove pull. A little contradiction there. Anyways, centrifugal, we'll call it gravity pull. And then we have centripetal force, which is, you swing the ball around, right? And this thing tends to push outwards. The only thing keeping it towards me, right, is the string. Other than that, the ball, if it's swung around, it wants to leave and go to another, out of the solar system. Okay, so what happens? The problem is they put centripetal force equal to gravitational force. That's a mathematical, almost a routine thing that they do, and it's deadly wrong. Dead wrong for the purposes of physics. This makes no sense in physics. In mathematics, could be. Mathematics, for sure. Physics, never. Okay, so let's find out why. Why you can't put those two equal. What happens is it starts here. They put force, Newton's second law, right? Force equals mass times acceleration, equal to the gravitational equation. This is a no-no in physics. You can't get away with doing this in physics. That's the problem. Okay, you can't do this in physics. Okay, so let's show why you can't do this in physics. Give me a second here. Here you have Newton's second law is mass times acceleration. Okay, and the gravitational equation is the gravitational constant g. It's a constant, so we can almost forget about it. We're going to talk about the other stuff there. Mass, big mass, little mass over r squared. What is r squared? Again, they should never use r. It's called distance, okay, not r. And that's part of the problem. The fact that they use r should never be used, should be distance. Okay, so that's the first thing I'm going to clarify. And we'll find out why. Okay, and so what's the issue here? Well, the issue is that the equation on the left, mass times acceleration, has to do with distance traveled. What the guy is doing there, with the little guy there, right? He's pushing the box. Okay, he's pushing a box, and what the mathematicians are going to do, they're going to look at his starting point and his ending point, and they're going to say, well, how many meters, how many kilometers, how many miles? They want a number followed by units. Okay, that's what mathematics does, and mathematical physics uses the same equation, the same notion. They say, well, we don't care about the qualitative part, the fact that he pushed the box. We want to know how many meters, how long was the trip. Okay, that's not what the gravitational equation is about. The gravitational equation, like the guy says, their little r radius, which is wrong. It should be distance. Okay, and again, you can't use radius because the Earth, compared to the moon, its radius, the orbit of the moon, for those of you who believe that the moon goes around the Earth, it changes. It's elliptical and so on. So you can't use radius because when you use radius, you're treating it as a circle. It's not a circle. You should use distance, okay? Because that equation gives you a single point. For that single point, you just look at that distance, okay? Not radius. And again, radius changes. And radius, the other problem with radius is that radius is calculated in meters and so on. And that's the other part of the problem. We're not going to be using units here. We're not going to be using numbers for anything, okay? We're going to look at this qualitatively. And we're saying that that equation on the left has to do with pushing, usually, right? Pushing a box from A to B. The other one has to do with the distance between A and B. And the mathematicians could never tell in the last 400 years, not a single mathematician picked up on this, that the distance, the separation between A and B is not the same thing as traveling from A to B. Why did they figure that out? Because in the religion of mathematics, distance, length, and distance traveled are synonyms. They don't care. They don't care about the qualitative difference between length and distance or distance traveled, because all they care is about a number. And the way they determine that number is by unrolling the measuring tape from A to B. No matter if it's separation, if it's distance traveled, or distance or length, right? They don't care. Because what they're going to do for distance, for length, for distance traveled is unroll the tip of the measuring tape, and they're going to count how many meters, how many kilometers, how many miles, or whatever. Okay, so this is the issue. Okay, so qualitatively, they're not the same, not in physics. So to put those two equations, one equal to another, they're comparing apples and oranges. Okay, let me get rid of this guy. So here we have the equation that mass times acceleration. Acceleration ends up being velocity squared over r, okay, for any star that goes around. I'm not going to derive it. You can very quickly look up on Google with at least high school level math. You can figure that out, okay? But acceleration is velocity squared over r, over the radius, okay? Okay, so again, we're saying those two equations are not the same. Let me get rid of this. Okay, so what's the issue with the stars? Okay, this is the issue. Here we have the equation that they come out of these two equations, right? One dynamic, which is the one on the left, the other one static, the one that's on the right, okay? And from that, they derive the equation at the bottom, which is the velocity squared is equal to the gravitational constant g. Again, it's a constant. We can almost omit that for the purposes of our discussion. We don't care about that if it's going to be a constant. We're concerned about the big M and the little r. What's the big M? Well, the big M is a big mass, for example, the sun, and the little m would be the earth. Or the big M would be the earth, and the little m would be the moon. And the same thing happens with a star. The galaxy, or the, you can say the perimeter, the orbit of a given star, anything within that orbit, all the mass that you find in there, all the stars, that's going to be the big M, meaning the galaxy. So that would represent the mass of the galaxy. And the star that's on the outside going around the galaxy, that would be the little m, okay? What is the r? It's the distance between the center of the galaxy and the star, okay? And what they're saying is that velocity of that star going around the galaxy is related, the square of the velocity. We don't care about the square because we're interested in the qualitative aspects here. But yeah, the square of the velocity of that star going around the galaxy is equal to a ratio of big mass, in this case the galaxy, over the radius of the star, the distance of the star from the center of the galaxy. Okay, so that's the story. Okay, now what's the problem with that? Well, it creates some problems for these people. Because here you have the situation, okay? Give me a second here. Okay, and what is it? Again, we have distance traveled is what you have embodied in that little velocity. Okay, that's what we have. That's the distance traveled, okay? And what do you have in the other side? Well, you have something different. You have distance, meaning separation. Okay, that's what we have there, okay? So I want you to keep that in mind, okay? And here we have a galaxy, okay? And so what are we talking about? We're saying that there you have the radius of that star to the center of the galaxy. Okay, that's that little r there. Okay, and here we have another galaxy. Let me get it up here. And it's got a bigger radius, as you can see there. Okay, so one is a short radius, the other one is a long radius. That's what I'm showing there. Okay, so what happens? If the radius increases, okay, we're going to increase the radius, okay, that radius there, okay. If the radius increases, then you can see what it's going to do to the velocity. As the denominator becomes bigger and bigger, that velocity, what's going to happen to it? Well, it's become smaller and smaller. Okay, so the velocity of stars on the outside should be slower and slower and slower. Okay, the farther you are, the longer the radius or the longer the distance between the center and the outside of the galaxy, velocity should be slower. That's what I'm showing there, okay? That's the point that I'm trying to make there. Okay, and so what's the problem with that? Well, the problem is that the chart that they built from observations of galaxies looks more like this. That the farther you are, instead of going slower, which is the expected there from the visible disk, instead of going slower, it goes faster, or if anything, stays more or less the same. But never does it go slower. And you say, how can that possibly be? It violates the equation. Okay, the equation said that the farther out you are, the longer the distance, the longer the radius, okay, from the center of the galaxy to a star, the slower it should go. And so velocity should drop as a function of distance, okay? And that's not what we see out there, okay? So this is the problem. And so they had to address this problem because they saw it in all the galaxies. And you say, hold it, all the galaxies? How do we solve this problem? Okay, and mathematicians, they came to the rescue. They always save the day, okay? And so here we have our equation again. Let me show it to you. Let's start here again. Okay, there we have the equation, our two galaxies, okay? And so what happens when we increase the radius? Okay, we're going to increase that radius, okay? And there we go. Let's make it bigger. Whoop, okay? And so now we have a bigger radius. Okay, so what happens? Well, velocity should shrink, okay? So how did they fix this problem? Well, this is where the funny part comes, okay? What they did was they started putting some things in there, okay? They started putting some mass. They said, what if we put more mass to compensate for the longer radius, okay? So that way they can keep it constant, or if you put even more mass, you can even get it to go faster. So what they said is, we're missing some mass. That's all that the problem is. That's the only way they could think of that they could fix this, okay? So they said, let's put some more mass. And what they said, but we don't see any mass there. Okay, so it must be dark. And they called it dark matter. Okay, so they say, okay, now I understand. There's mass out there. I can't see it, so we'll call it dark mass. And better yet, let's call it dark matter because it's got to be some kind of matter. Remember, matter is mass, matter has mass. Or matter has mass. Okay, so what they did is essentially this. They sprinkled this dark matter on the outside of the galaxies to produce the necessary mass, okay, the mass that they needed for the equation to come out right. This is all about equations, okay? And so here you see the chart now. If you sprinkle a lot of kilograms out there, only out there, not inside the galaxy, then yeah, you can produce the result. It's like, this fixes the problem, doesn't it? We can't see the stuff that's out there, but if we sprinkle these kilograms out there, okay, then obviously, you can produce the effect, the necessary effect that matches what we observe. The equations now match what we observe, and we're just going to call it dark matter. And so what they did after that was say, okay, so we have our dark matter. Now what we do is we look for it. So now they have the dark matter. They proved dark matter. They couldn't think of any other reason why the stars on the outside would go faster than the ones on the inside. So they said, okay, it's got to have a mass. What else could it be? That's the type of answers a mathematician give you. A star rolls around nothing. What else could it be except a black hole, right? A lot of mass in the center, and the star is rolling around this inexistent singularity. What is dark matter? Same thing. We don't know why the stars on the outside go faster. Very easy solution. Let's sprinkle some mass there on the outside of the galaxy. I don't know why this dark matter is only on the outside of a galaxy, but that's where it's at. Why? Because that's where they need it, in order for observations to match the equations, or for the equations to match the observation. So they have here the observation. They say, this is what we observe. How do we fix it with our equations? Very simple. Let's put some mass in there. And they called it dark matter. So dark matter is an equation. They've never seen it. And they already confessed that. They said, we've never seen dark matter. So they don't see dark matter. It's not really dark. It's invisible. It's more than invisible. It's translucent. You can see right through it. Transparent, translucent, you can see right through it, because we can see stars in the background right through the edge of a galaxy. And so you say, well, hold it. With all these galaxies behind it, we can't see it even. I mean, if it's dark and suddenly, you have the disk of a galaxy, suddenly, with another galaxy in the background, or stars in the background, that you should be able to see the dark matter. Say, oh, there's the dark matter. Like, when you see Mercury or Venus go across the sun, it looks like a little dark ball. Well, this is what you would see if you're looking at the edge of a galaxy, since all galaxies have dark matter on the outside, right? So anyone that you look at, you should be able to see the dark matter. All we have to see is some kind of star or some kind of galaxy in the background that kind of puts a little contrast there. We should be able to see all those little stars, all those little balls of dark matter, just painting the outside of a galaxy. We should be able to see it. And they haven't seen it yet. None of it, okay? So what happens? They gave the task to the accelerators, to the LHC and to all these other accelerators. They're looking for all this stuff. And here you see what the LHC tells us, the CERN, the people who do accelerations here in Switzerland. And what they do, they accelerate particles, or so they think they do, and they smash them. And from accelerating and smashing them, they purport to explain dark matter. They expect to find dark matter and explain how our universe works out there. Okay, so we're going to figure out what happens out there in the galaxy by accelerating particles here, in the accelerators. And what's the issue there? Well, the issue there is that, remember, dark matter weighs a lot. They say a little grain of dark matter weighs tons. And there's lots of that out there because you need lots of it out there to make sure that the star travels fast around the galaxy, right? So they have to sprinkle a lot of this stuff. Now they want to find those grains of sand in the accelerators. And so here's the LHC. This is what they say: breaking new ground in research for dark matter. So now dark matter has entered the accelerators. The Large Hadron Collider, LHC, is renowned for the hunt for and discovery of the Higgs boson. But in the 10 years since the machine collided protons at an energy higher than previously achieved at a particle accelerator, researchers have been using it to try to hunt down an equally exciting particle. Remember, this is a particle, a hypothetical particle that may make up an invisible form of matter called dark matter, which is 5 times more prevalent than ordinary matter and without which there would be no universe as we know it. So if dark matter collapses, if that religion, falls down the drain, well, then we wouldn't have a universe. Okay, so dark matter had better be true. Otherwise, all the theories about how our universe works, disintegrating overnight. The LHC dark matter searches have so far come up empty-handed, as have non-collider searches, but the incredible work and skill put by the LHC researchers into finding it has led them to narrow down many of the regions where the particle may lie hidden, necessary milestones on the path to a discovery. Okay, so they continue with this. It's important to hear what these people have to say. The LHC has really broken new ground in the search for dark matter in the form of what? Weakly interacting massive particles. Why? Because they say that this dark matter weighs a lot, is invisible, but does not interact with matter. And we're saying, hold it, we got a problem. What do you mean it doesn't interact with matter? If it doesn't interact with matter, how is it that it affects the speed of stars? I mean, if it doesn't interact with a star, why would it push a star to go faster? That's the issue. If it's not interacting with matter, what's the point of having this heavy, invisible particle out there that doesn't interact with anything? Yeah, what does it interact with then? But continuing here, says, by covering a wide array of potential signals predicted by either production of dark matter or production of the particles mediating its interactions with ordinary matter. So this stuff is not ordinary matter. It's very heavy, it's invisible, but it doesn't interact with matter. Great. I hope they can find it. It sounds like they're talking about a ghost. That's what I think they're talking about, spirits. The results have prompted theorists to rethink existing ideas for what dark matter could be. Yeah, I mean, what is it? I mean, does it have shape, this dark matter? Does it look like a ball? What are these people, can they draw dark matter? What are we talking about, a bunch of balls, little balls there, little beads? Heavy, no, obviously. To look for dark matter, the LHC has been trying to make it by colliding beams of protons. Some experiments are using telescopes in space and on the ground to look for indirect signals of dark matter particles as they collide and break themselves out in space. Oh yeah, good luck with that one. They're looking for ghosts that are hitting each other, right? They're going to crash against each other. Maybe, I hope they don't go through each other, because if they're translucent, if they're invisible, they're dark but invisible, right? Or again, translucent. If they're very heavy but they don't interact with matter, maybe they might even go through each other and you'll never see them collide, right? I mean, why would they collide? Others still are chasing these elusive particles. Absolutely, they're chasing them, right? Directly by searching for the kicks or shakes they give to atomic nuclei in underground detectors. The main signature of the presence of a dark matter particle in such collisions is the so-called missing transverse momentum. To look for this signature, researchers add up the momenta of the particles that the LHC detectors can see. More precisely, the momenta at right angles to the colliding beams of protons, and identify any missing momentum needed to reach the total momentum before the collision. If the total momentum after the collision is not zero, the missing momentum needed to make it zero could have been carried away by an undetected dark matter particle. Yeah, it could have been carried away by an angel also. I mean, I don't know what these people are doing, and you're paying for it. This is paid for, by tax dollars, because if the tax dollars of the U.S., for example, don't go to CERN or LHC, it still goes to SLAC and Fermilab and Brookhaven and all these other colliders, and they're doing the same thing. So yeah, your tax dollars are paying for this nonsense. These people are looking for ghosts. They defined it as a ghost. It doesn't interact with matter. Sounds like a ghost. The ghost, as far as I know, doesn't interact with my curtain. Some people say it does, but these people are saying it doesn't. It's very heavy. It's very invisible, very translucent or transparent. And so what are we talking about? It looks like we're talking about a ghost. This is a phantom they're looking. And of course, when you're looking for a phantom, it's very hard to look for it with a telescope or by smashing them. Because again, if you smash a ghost against another ghost, and they're both transparent, translucent, maybe very heavy, but they don't interact with matter, maybe they don't even interact with each other. I think, Casper would go right through one of the other ghosts without any problem. So I don't know. I don't know what these people are looking for with your tax dollars, okay? Okay, so here we have, this is what the LHC does. It accelerates particles, okay, down the beamline, and they're going to send them all around, the lengthy accelerator there. And they're going to make them collide at some point. So this is where they plan to find the so-called dark matter particles. Here's the collision, okay? So you go in there, you smash two of these dark matter particles, I guess, or they can smash protons. I guess they're going to produce the heaviness of a dark matter by smashing protons against each other. I have no idea what they're trying to do here, because if they're going to smash, for example, protons, as they've been doing, to try to get a particle that's out there in space which weighs tons, I'm not sure you can do it with a proton which doesn't weigh as much. Unless maybe they say, well, it depends on the energy with which we accelerate them, okay? And yeah, if the notion there is that energy has to do with mass. It's another form of mass. If you put enough energy in the gazillions of whatever units, keV, okay, or gazillions of electron volts. Yeah, if you smash two of these particles at great speeds, which is what they're talking about, maybe they can produce the weight, the mass of one of these dark matter particles. And when they smash them, they're going to tell you, look, it looks like that. Because I'm sure they're going to find it. And they're going to say, look, there we smashed two of these particles, and this is what we got. And they're going to say, see all those? Those are each one of those little guys out there. Those are the dark matter particles rushing away from ground zero. So this is the way they're going to handle it. Believe me, these people are going to find, without any doubt, they're going to find dark matter, or their name is not Albert Einstein. Okay, so yeah, they can't fail. Okay, it's too big to fail. Okay, how do we do it in science? All this dark matter stuff. Well, it's very simple, and I hate to put it because it's just going to embarrass these people later on when they see it. I mean, they made a monster out of this whole thing, a mountain out of a molehill. Okay, here's oh, by the way, this is just a comment by a guy at the LAC. He says, dark sector scenarios, meaning dark matter, right? All this studying that they're doing, all these evaluations, provide a new set of experimental signatures, and this is a new playground for LHC physicists. Yeah, you're paying for these people to play. They've got all these games that they're playing out there. They're trying to accelerate protons at great energies. It doesn't accelerate the speed, but for some reason it imbues a lot of mass to the protons when they smash them. I guess some particle comes out there that is heavy enough to be called a dark matter particle. And they say, we found it. Here it is. They bring it to you. Here's the dark matter. We found it. I know. Sorry, it's got to be dark. It's got to be more like this. Okay. Anyways, how do we handle this in science? Again, genuine physics. Okay. So here goes. Again, I hate to embarrass these people, but here it is. Okay, we're saying all stars are physically interconnected. We don't pay attention to mass. We don't pay attention to equations. We don't care about those. We just say that if all stars are physically interconnected, we have a physical mechanism, first of all, for why stars are not flung out of the galaxy. That's the first issue. The second one is that, stars on the outside, you can see why they would go either faster or at least at the same speed as the ones on the inside, because the whole thing rotates like a carousel. That's why. Okay, the whole thing spins around as if it were made of a single piece. Okay, because they're all interconnected if all atoms in the universe are interconnected. Okay, so that's the first issue. And just in case, we reinforce this by showing the galactic magnetic field. Okay, here it is. So not only does a galaxy spiral around, but it's perpendicular to it. We have the magnetic field of the galaxy. Okay, and very easily to imagine that these magnetic fields, they have to stretch, incredible amounts of distances. Imagine the magnetic field of the sun stretches beyond Pluto. And people say, how can a magnetic field go that far out? And yeah, and it does. It's already been measured and so on. So the magnetic field of our star actually protects us from, interstellar influences of all kinds. And it's very likely that if you put several of these galaxies, one with respect to another, their magnetic fields probably interact. And where they do, maybe we can see some fancy things going on, like maybe black holes, because you have all these galaxies, all these with strong magnetic fields, and where all these magnetic fields meet, there should be some interesting phenomena going on to stars that are caught in that region. Okay, because we're talking about magnetic fields. What are they? They're threads that are swinging around the galaxy and hitting, essentially, or sweeping by stars. And remember, a star, has electricity and magnetism. Those magnetic fields that you see in the sun. What is that? It means that there's some electricity going on inside or at least in the surface of the sun, producing those magnetic fields. So we have electricity and magnetism, and here you have the magnetic field of threads, right, of the entire galaxy sweeping down on this little charged ball. And yeah, it's going to swing it around. It's going to do things to it. And so, yeah, we have to look at this in physical terms, and the physical terms are threads. That's what physical is. When you use words such as mass and field and energy, you're not talking about physical entities. So you cannot explain how the universe works, the workings of the universe, gravity, electricity, magnetism, right? You cannot explain it with concepts. You got to use physical objects. You got to identify the invisible, intangible physical objects that are out there. And in the case of dark matter, very simple. Dark matter simply is an inexistent equation. It's an equation for inexistent objects, things that are out there. What are out there is that all atoms are interconnected, and that means all stars are interconnected. That's the reason stars don't fly out of a galaxy. They're not flung out of the galaxy when the galaxy spins around. If you add to that the magnetic field of the galaxy, it maintains the integrity, or helps to maintain the integrity of the whole galaxy. And that explains why, all these galaxies don't break apart, and you see them as, when you see these up-close pictures of these galaxies, what you see is gazillions of stars just twirling around the center. That's what a galaxy is. What you don't see are the ropes that interconnect every one of their atoms, and you don't see the galactic magnetic field, even though even the mathematicians accept that there is a magnetic field. They just don't pay any attention to it.